Welcome back, everyone. In the last video we demonstrated how you can make use of the Orange software to actually do some really quick and dirty analysis on small data sets. So what we're going to do this time around is just to demonstrate how you would do the whole dimensionality reduction by using the PCA. So for a start, you can actually get these data set directly from the UCI machine learning repository. Just basically download the wine.data. All right, so we need to import the usual library. Okay, just wait for that to download. In the meantime, I'm just going to read my CSV type away since my typing is so fast. And we just have a look at the shape itself. Looking at this, same as what we had before, when you actually look at the Orange 178 samples, 13 would have been the actual features and the 14th would have been the target itself. So let's have a look at the data first before we actually type away. Alright, so this is what it looks like. So the column 1 called class, that would be the type of wine. So we're going to store the data into from 1 onwards, because we do not want the 0. Okay, and it doesn't like it because I had a typo here. Okay, and why? Our target would be class. Alright, that's good. Now the next thing that we really need to do, or want to do, is just split our data. Scikit-learn .model selection, import the train test split and the X train, and then you have the X test, and then you have the Y train, and then the Y test. Let's go to the train test split, and we have our X, and then we have our Y. The test size is 20%, and we forgot the comma, and the random state. Let's go to 42. Okay, that's good. So remember, I mentioned this a few times. The PCA is really quite sensitive to scaling, so it's crucial that we do scale our data. Otherwise, you're going to have very, very different results and possibly some issues as well. So from scikit-learn pre-processing, okay, that's why pre-processing. Import and standard scalar. Let's instantiate this standard scalar st, and okay, right. Now that we've done that, we just need to scale our data X train scale. I'll just call it as that, as the fit and transform at the same time, and X train. Okay, so we're going to do that for the Y train, and we're going to call it the transform data, call it Y underscore train underscore SC. So we're going to fit transform the Y train as well. Nope, you don't actually fit the Y train. There isn't actually a need to do that because in this case, it's an unsupervised. I just got into that typing mode and completely not paying attention to what I'm doing, so forgive me for that. So it's actually X test that we're doing, X test. Okay, right. Now it's the PCA, the components. Technically, you don't want to do that as well. I'll come back and explain that later. So PCA, the components. Now we can actually borrow the idea that we did earlier and call it 2, all right, because that's what was actually provided for earlier. So at least we know, but I'll show you how, if you're actually working with a completely unknown data set, what you can actually do. So PCA, right, we do need to actually import PCA. Okay, so we left out this line. Okay, that's okay now. All right, so we've selected number of components to 2, or principal components that we're looking at. So let's just have a look, just print the result itself. I'm gonna round this, otherwise it's gonna be quite ugly. Okay, don't believe me, I'll show you. So the PCA explained variance ratio. Okay, it's a little bit hard to read, isn't it? So that's why I like to, print and use the numpy and just round the number PCA explained ratio and just round it to 3 decimals. That's much easier to read, right? Yeah, the first principle explained 35.9, and then the second component explained 23.6. Okay, now having done that, what we're going to do next is actually just look at all of the components itself and see how they actually, two components, how the composition of it with the original 13 features that we have. So how do you do that? So you do data frame, and then you round your PCA components, and we'll use 3 decimal as well. Now here we go. So the only issue is that we have 0 to 12, and it doesn't mean much. What we're gonna do is come up here and look for the name. This is X. Okay, so we can just use X. Data frame, and then the columns. This should do. Okay, there we go. Right, so we now have the actual name to go with it. We have the alcohol, the malic acid, the ash, and you can see the breakdown. Of course, you can do it this way as well if you like. Principal component 1, principal component 2. Earlier, I do remember we were looking at the flavonoids. It actually was quite important. Yes, it still is important. It is still the most important components in terms of the for the explain the variance itself. Right, now remember I said that because we cheated, we used orange, we were able to tell that 2 components is actually okay, it answers some of the problem. What if we actually do not know? This is what you would do. PCA is equal to PCA. Number of components, we would set it to none. Oops, not equals, none. And we're gonna fit the X train scaled, standardized or standard scalar. Okay, having done that, this is what we do now. Okay, we fit transform and the X train C. Right, and after we've done that, the next thing we do is just have a look at what we actually did before. Round PCA and then explained. I'll come back and explain a little bit more. And 3. Right, earlier we had this 2. Okay, and what happened if we actually have it all the way here? Plus, not pretty, plus 86%. All right, so that explained 86%, or the first 1, 2, 3, 4, 5 explained 80% of the so-called variance or variability. Of course, you can do this. You can do cube sum of this. This is what you get. 1, 2, 3, 4. 4 is already 81. 5 give you 86. Okay, so I hope that actually gives you a fair idea of this is what you can do in order to actually transform your data from 13 features down to 2, and from 2 or 3 or however many that you want to select. But the basic idea is that now with 4 components, we are able to actually explain 81 or 82% to be specific of the variability of the data itself. Okay, so what we like to do now is just to relate the actual result itself and try to look at the so-called what is the best way to actually select the number of components. I show you how you can do this with the cube sum. That's one way to do it. The other way is that you can actually plot this out just to actually give yourself an idea of how it would actually perform overall. So let's just plot that out. So PLT plot, it's always easier to visualize. So let me just do this. But I'm going to do something slightly different this time around. I'm just going to multiply that by 100. It's always easier to read percentage with 100. Most people prefer to do it that way. Let's make this nice and pretty. We have the X label. We call it number of components. And the Y label, and we're going to call it the cumulative explained variance, and scratch whatever the output is. And there you go. All right, so you have 0 gives you 40, 1 gives you roughly about 60 something, 2 gives you around 70 something, the third one already gives you 80 something, and the fourth one 86%. If you want the specific numbers, it's actually here. So from this visualization, you can actually straight away tell well, how many components you would choose will be sufficient to achieve your ultimate goal of dimensionality reduction. So with that, that's really the basic lesson I want to cover here on dimensionality reduction using the PCA. Alright, I was gonna come up with an exercise for you to do, then I realized something when I was looking through my codes. There's some correction that need to be made. I've accidentally used X-test here. Now, I do realize that earlier I did actually have a line here that actually fit transform. Where was it? Fit transform this line here. There was an extra line here, which is X test underscore sc and then sc dot fit transform the X test. Technically, that's not really the right way to do it. You are supposed to use the X train transform, or first you fit sc and fit the fit the X train, and then from that you use the sc to transform the X test. So let me just show you this. The proper way to do it is, first of all, you fit it X train, and then you do the actual transform of the X train itself, and then store the X train sc. Now, having done that, then the next thing that you should do with the X test underscore sc is sc dot transform and the X test. Okay, that will be the right way to do it. Now, whereby earlier the code was actually this code, and I'll just change this, and let me just make a label, wrong approach. Okay, the reason is this. You don't know what the X test data is supposed to be. When you're scaling it, you want to scale it to the actual training data. Because in the real world, you're never going to see the actual data that flows in. So everything that you've done, the scaling, the transformation, the fitting was all done in the X train itself. So when you come to the actual X test that comes along, all you do is just transform it using the mean, the variance, all of the information that originally was captured within the X train to transform the X test. You will never ever fit the X test. But doing it that way will mean that you will have a completely, well, garbage in, garbage out is probably the best way to describe that. Okay, so coming down here, that will mean that these are correct now, but rather for now, for our exercise, we just keep it at X train, because we don't, technically with this principal component analysis, we don't actually need to split it into X train and X test, because we're not really trying to actually model it right now. We're actually performing principal component, or the dimensionality reduction, which is not really fitting a model per se. Okay, so let me just rerun the whole thing, clear everything and rerun again and see if there's any errors. And then after that, I'll give you the actual project for you to do at the end of this lesson. Okay, so that's all done, all clear now, all sorted. There's no issues anymore. I'm going to leave that code there so that you can actually refer to it. Okay, so this is the assignment for you. I'm pointing to the so-called web page you can go to actually get this source data, but at the same time I've already actually downloaded and I will provide it as a zip file for you. What I want you to do is that this abalone dataset has 8 features. Let me just try to recall. Yep, it has 8 features. Now, by applying PCA, how many principal component would you need to achieve 80% explanation of the variance? Okay, so try to actually follow the steps that I've shown you before, and don't peek at my answer. I'm going to give you the answer anyway, but don't peek. Just do this exercise to help you to understand and learn how the process is done, and it actually really helps you to capture the understanding and appreciation of the power of PCA. So out of the 8 features, after it's been transformed with the principal components extracted, how many PCA components do you need to achieve 80% variance? So that's really the exercise. So let me summarize this lesson. What we've done here with the after watching the orange demonstration of PCA, we did likewise with the wine dataset. We downloaded it, we transformed it, and also show you the wrong way to transform it, and then we imported the PCA to just basically do the decomposition or dimensionality reduction, and we try fitting it again. This time round, well, made a mistake there. This time round, with no preconceived idea of the number of PCAs we want. Okay, so that's just a notation for us to actually run the whole thing, and that basically transform the whole thing. Well, basically we want to transform the train and look at the actual explained ratio and also the explained variance ratio. Okay, so yeah, so that's really what we cover, the PCA itself, how to use it, basically finding the actual ideal place or ideal number of components that you should include. Here 4 is the ideal number. In this exercise of ours, anything more than 80% is depending of course on the situation, but for our exercise this is sufficient for our use. With that, I'm going to end this lesson. The code's there. You feel free to actually go through it and compare against what you actually have done as an exercise. Thank you for watching. In the next lesson, we are going to continue with this project wine and choosing the number of components. I look forward to seeing you then.